Okay. Today we're very privileged to have Igor Pak from UCLA, and he will talk about random linear extensions of posets. Take it away, Igor.
Oh, thank you, Ben, and thank you so much for inviting me. It's a pleasure. I'm going to talk about, the talk is going to be half combinatorial, so I'm sorry for those of you who are prepared for mathematical physics or some hardcore probability. I'm going to talk, so in fact, in much of the talk, not much of the talk, but in the beginning of the talk, I'm going to define a whole bunch of combinatorial notions related to posets and linear extensions. And then I'm going to start presenting our results on sorting probability, first classical results, and then some of our results, not including results from last year that were proved from for sorting probability for Young diagrams, and later for very recent result we just posted on the archive related to the cross product conjecture. So unless there are any questions, I'll move on. Are there any questions? Well, sounds like a no. To me. So, all right. So linear extensions of poset, and so by let P be a partially ordered set. On the ground set is going to be X with n elements, n is going to be finite, and I'm gonna define linear extensions as you can see over there. Linear extension is just a bijection from the ground set S to numbers 1 up to n, which satisfy the following properties. F is a bijection and F is order preserving. That is, for all x less than y, we have f of x less than f of y. And that should be true for all pairs of elements x and y in the ground set. Is everyone okay with that? If that's going to be our main definition. And I'm going to denote by E of P the set of linear extensions that's this curvy E, and the little e of P is the number of linear extensions of poset. So here are a couple of basic examples on this. So if you have a partially ordered set with no relations whatsoever, we have n elements. Linear extension can be any permutations. In this case, there are n factorial linear extensions. And similarly, if you have this kind of tiny poset on 4 elements, then there are 3 linear extensions which sort of look like that. I'm thinking that oh, let me draw this. The way I'm viewing this is that my order numbers which are above are smaller than the numbers which are below. Is everyone comfortable with that? That's an example. Let me know if you're not. This is a really good time to ask a question, because if you're lost here, you'll be lost forever.
Well, that's not the usual convention, right?
Yeah, that is. I just like to draw them from top to bottom, okay. But I think you can just turn the whole talk upside down if you want.
I will.
Sure. I write from top to bottom, so I draw posets from top to bottom.
Flip the symbol of your inequality. It's no different.
Say it again?
Just flip the symbol of your inequality as equivalent here.
Okay. Well, this, I think we exhausted that joke to death, so let's move on. I'm gonna talk about a whole rather large posets. So let me give you a few large examples so that you can have something visualized. So Anna, how do you draw a tree? I bet you draw the trees the same way as I do, even though in reality trees grow up, not down.
Yes, I would draw it the same way as you.
Okay, so if you have a poset, so for every tree there's a poset. Basically, you take a root of the tree to be the minimal element in the poset, and the numbers will be increasing downwards. And it is a classical result in enumerative combinatorics, but it's really more of an exercise. That number of linear extensions in this case is, let me maybe make a nice box for this, is given by this product formula, where on the bottom you see numbers b of x. That's a branch number, the number of elements in the poset, or equivalently vertices of a tree, which are bigger than the vertex that you began with. Okay, everyone okay with this formula? So that's the first one. So let me, before I move on, let me maybe explain what does that really mean. Not as much then as you think. So let me explain what does that mean. What that means is, how do you get a product formula? The way to think about it is to think of a random linear extensions of this poset, which basically means a random random ordering 1, 2, 3, 4, 5, 6, 7, 8. And the way to understand that is to understand that the probability that this element X is the smallest in the branch is equivalent to saying that this is a linear extension. So if you take any random permutation of labeling, all we need for this to be a linear extension is X to be smaller than everything else. And what this formula is saying is that these events are independent. So if you have X and Y here, then the probability that X is the smallest in this branch is independent on whatever is going to happen for the branch which is below Y. That's what this formula means. And it's really easy to prove for trees, but the corresponding formula for the poset formed by Young diagrams, in this case, the ordering goes down and to the right. The corresponding formula for Young diagrams is called the Hook-Lang's formula, and this is really the reason why I personally started working in this area. That's basically one of my most favorite formulas. What this is saying is that there is still a product formula for the number of linear extensions of this poset. Linear extensions are called standard Young tableaus, but let me not define them carefully. They are the way what you think should be. So this filling of numbers, filling of the diagram with numbers from 1 to n, which are increasing in rows and columns. And one can try to get a similar proof, but it's not going to work. The similar proof to the trees. So finally, for the Catalan posets, these are just diagrams of 2 by n, and in that case, number of standard Young tableaus is a Catalan number, and we all know and like Catalan numbers. So that is a large example that we're going to work with later on. Any questions so far about any of that?
The number of the linear extension here is the same as the definition of the poset order dimension, right?
I don't know what the question is asking. I'm sorry.
So here you count the number of the linear extensions.
I can tell you what linear extension is again. Linear extension is order preserving bijection. And in this particular case, order preserving bijections are standard Young tableaus of the shape of that Young diagram.
Okay, thank you.
Sure. So now I want to talk about complexity aspects of that. Peter, you still here? Yes. So your name is appearing right on the top here. So this is a truly classical result by Brightwell and Peter Winkler, which is saying that computing number of linear extensions is Sharpe complete. Now, this should be understood as a difficult theorem, in contrast with many other results about Sharpe completeness. So, for example, number of, I don't know, Hamiltonian cycles in a graph is Sharpe complete. This result is difficult because it doesn't correspond, because the corresponding decision problem is actually trivial. There is always a linear extension of a poset. That's not a trick. So proving that the number of linear extension is Sharpe complete is actually quite a bit more difficult theorem. And it's also more difficult because in this case, there's something called Pras. So I'm writing that on the bottom here. So what this is saying is that the number of linear extensions can be approximated within a factor 1 plus minus epsilon in time polynomial in n, and that means that it's actually very, very different from anything you're going to see for like counting number of 3-sat solutions and so forth. So this is this problem of computing number of linear extension is actually a very tricky problem. And for many classes it is in P, but for those, but in general it actually can be done in is actually sharply complete. And let me advertise my own result. This is a joint work with my former student Sam Dittmer. So we proved that number of linear extensions is sharply complete for 2 more classes. It's just for poset of height 2. This is the example of a poset of height 2. And for poset of dimension 2, this is just basically posets obtained by putting bunch of squares into the plane, in this case n squares, and having the ordering the similar one to the ordering for Young diagrams. Is everyone okay with this? So somehow the bottom of the slide got cut off, but any questions about any of that? So the way, and it's actually good since this cut off, let me just say what it says. It says that the way to do it is by to approximate this number is to run a Markov chain on all linear extensions, where you pick an I at random and try to swap I and I plus 1. So either it works or it doesn't. If it doesn't, then do nothing. If it does, great. Run this Markov chain for a while. Turns out that this has a polynomial mixing time. Just kind of amazing result. And was obtained in 91 kind of independently by Matthews and Karzanov-Kachin. Everyone good with this?
Distribution uniform for that Markov chain?
Yes.
Is it straightforward how you bootstrap it from that to getting a count?
Yes. That's because everything is self-reducible here. You can just remove element n and get a smaller poset.
Okay, right.
I'm sorry, I don't see actually who's asking me questions, so I'm answering in sort of the space. Let me move on. So I also want to mention some complexity aspects of this, and by that I mean positive result. So in fact, there are 3 classes I want to highlight. It's very easy to calculate the number of linear extensions of poset for serious parallel poset. I'm starting from the bottom. Serious parallel poset are the ones where you obtain which is defined sort of inductively, kind of like so if 2 posets, so a poset with 1 element is serious parallel, and then you can make posets in parallel or sequentially to go like this or like that, and the numbers are really easy to compute in this case, and that's a really nice class. Another nice class is the class that I personally like, is very much is the class of skew shapes. So when you take one big Young diagram, remove another smaller Young diagram, in that particular case, there is a phi determinant formula, which those of you who do algebraic combinatorics know quite well. There is a determinant formula for the number of standard Young tableaus of this skew shape. And finally, the class of posets of width d. So that's so the way to think of that is you have d chains from top to bottom, and then some relations between them. So it's a Dilworth theorem saying that you can decompose each such poset with maximal anti-chain d into d chains. And in this case, one can use dynamic programming to calculate the number of linear extensions of this poset. This is also not so difficult. So that's basically the end of combinatorial story. Is everyone happy? Can I move on? This is a good time to ask a question. Okay. There are no questions. I'll move on. So this is where the sorting probability story starts, and I'm gonna need to define it. So the way we're gonna do it is for every poset I'm gonna define a parameter delta, where delta is gonna be equal to the minimum of the probability minimum over all pairs of elements x and y in my ground set of a difference of two probabilities. Probability f of x is less than f of y and f of x is greater than f of y. Okay, so basically the closer the probabilities are, the smaller is delta. Okay, in the extreme case, when x is the minimal element, y is the maximal element, one is probability 0, another one is 1. So delta, so that is not very small number. That's 1. Okay. Understood? Everyone good? So now we have a one-third to third conjecture, which is motivating a lot of work in the area and somewhat partially motivating our work. So what the conjecture is very simple to state. The state is saying that for every finite poset, this delta of p is at most 1/3, which if you convert this notation into the probability, this is saying that there exist two elements in my ground set, so that the probability one is that linear extensions at one is less than linear extension at another is between 1/3 and 2/3. Now this p is is a probability defined over uniform linear extensions of my poset. Okay, so we take a uniform measure on all linear extensions and are asking, does there exist two elements for which kind of split the measure into two not exactly equal but somewhat comparable parts. I'm going to wait for a second to see if there are any questions about the definition of sorting probability and one-third to third conjecture.
Igor, I have a question. This is Dan.
Okay.
Is there anything special about the numbers 1/3 and 2/3?
Yeah, that's because that's the best you can do. If you take a poset with, let me try to draw it. If you take a poset with which looks like that, kind of. In that case, it's exactly 1/3 and 2/3.
So, for example, for some of the classes that are listed in that theorem at the bottom, is it also sharp that 1/3 and 2 that you can't do any better than 1/3 and 2/3?
Yeah, this is a poset of width 2. So for posets of width 2, this is the best you can do.
Okay.
And it's also poset of height 2 and so forth. This is the and series parallel poset. Essentially, this conjecture is understood for posets which are nice. For general poset, it's open, but for nice posets, it's understood that there's a whole list, basically poset of width 2, posets of height 2, series parallel posets. Those are classes that I talked about before, and some of them, many of them, contain this one. So, for example, if you really like skew shapes, then take that skew shape. 3, 1 minus 3, 1 minus 1, 1, and that is exactly the same as my poset, as my little poset p over there. Did I answer your question?
Yeah.
Okay. So the point is there's a large amount of literature on that, and something that's going to be important for us for skew Young diagrams. That actually was done by somewhat of an ad hoc argument by Olsen and Sagan. What I can just tell you the idea of what they do. They take a poset and look at the boundary, and the boundary somehow you can sort of catch two chains on the boundary, and those are two chains, and then that goes straight into posets of width 2, which have to change. So essentially they're reducing a problem for skew Young shapes to posets of width 2 by boundary trick. That is the idea. Is everyone okay? I'm just going to move on unless somebody interrupts me and says me stop, Igor. Okay, no one wants to take responsibility. So here is a bunch of results that's important for us. The first result was a major breakthrough in the field. The way it works is the following. So what Jeff Kahn and Saks showed that this probability delta is actually bounded away from 1. So instead of 1/3, they proved 511, but that's already just a fantastic achievement. And this was later somewhat improved by Brightfield, Felsner, and Trotter to 1/√5, which is marginally better. This is 0.45. This is 0.44, and that's where the conjecture stands, and likely to continue to stand for a while.
I think that should be 3/11, Igor. 5/11 would be better than 1/3, 2/3.
What?
No.
I think you. I don't know who's speaking to me, but whoever you are, you might be confused. Proving that the probability is between 3/11 and 8/11 is weaker than proving that this probability is
right.
3/9 and whatever it is, 2/3.
Okay, I was looking at the 5/11. Okay, that's something else, I guess.
Okay, good. So 5/11 is the difference between the two.
Oh, I see. Gotcha.
Not okay. Good. So let me mention this important result by Kahn and Kim, who basically say that in fact one can use the tools from the Kahn-Saks result and show that it's and do more work, and then show that this implies that one can sort numbers if you're giving your poset as a partial information. And sort in the optimal time, which uses log of number of linear extension comparison. The main difference here with the conjecture is that this basically requires one to be able to efficiently find elements X and Y in the sorting probability. So here X and Y just said there exist X and Y. And in the Kahn and Kim paper, they basically are able to find X and Y for which everything works. Everyone okay with Kahn and Kim result? And let me also mention this conjecture by Kahn and Saks from the same paper, where they're saying that if the width of a poset is growing, then the sorting probability actually is going to converge to 0. So in fact, they're saying that the small posets are the posets where you can have 1/3 or some non-trivial constant. If you have a very posets of large width, then this is not going to happen. Where width is the size of the maximal anti-chain in the poset. Am I being too fast? I want to get eventually to our results, so bear with me. Any questions at this point?
So I was going to ask earlier if there are like a family of tight examples, not just the one you showed. But I guess this conjecture implies that there can't be families of tight examples that have arbitrary width. But are there like?
That's correct. In fact, if the posets of width 2, Eichner showed that and it doesn't have kind of like irreducible component to this tiny poset of size 3, then it's strictly bigger than 1/3, and there are even better bounds now.
Okay, so it's believed that that was the only example that's tight. That's that poset you showed.
I suppose. Again, what we're going to do is going to be somewhat more narrow and much stronger. You'll see. Any other questions?
Igor, I have a question. This is Luis. So
Hi,
the Kahn and Kim result is a deterministic algorithm, is it? Well, I guess the reason I ask if maybe it's because if it was randomized, that wouldn't be so interesting, because couldn't you just pick the next pair to compare at random or something like that? And
No.
They found, did they, I guess my question is, did they find a deterministic algorithm to find the next pair or not?
So, yes, I think so.
Okay.
But it's been a while. I don't remember.
That's okay. Yeah,
The proof is geometric, so they're not they're not like picking pair of elements at random. This is really something that needs to be done very, very carefully. It won't work if you pick it at random.
Okay, makes sense. Yes.
Okay. So this is so finally we're getting to a place where our names are, and let me underline our names. This is Swihong Chan. He is currently a postdoc with me at UCLA, and this is Greta Panova, and she is also here somewhere, most likely invisible on this chart. So let's see. So and essentially everything I'm going to say is going to be joined with them. So everything new. So here is the first result. The first result is dealing with skew shapes, and there are two conditions that I want to satisfy. So the first condition is I want to have bounded number of rows. So number of rows is going to be D. That's a bounded number of rows. The second condition is let me do it in red. I want to make sure that the rows are actually distinct. Not just distinct by a factor of epsilon, so that you can sort of see it drawn over there, so that each row is bigger than the next row by a factor of by at least epsilon n. We have other results, but I think this is the most attractive one. And in that case, we're saying that the sorting probability behaves like 1 over square root of n. So not only you can find two elements which divide into roughly equal, meaning at most one equal to twice the other, but in fact you can make sure that these two squares are very, very close to each other. That the probability is going to be within 1 over square root of n from each other. The probability that you see in complexity aspect, the probability that you see over there. So those probabilities are going to be very, very close to 1/2, which means that they're going to be very close to each other. Probability greater and smaller. Is the theorem clear? Everyone okay? Okay, good. So let me give you a very hand-wavy, in the most hand-wavy way possible, idea of what do we actually do for that, because that's not something that I can even explain in one talk at all. But the general idea is not so bad. The general idea is that the way we're thinking of standard Young tableaus in this case is as if they were paths in a d-dimensional space. Then what we do is we pick two elements and we project this path. Sorry. What I mean is we pick two rows and then we look at the projection of my path on these two rows. That picture is two-dimensional now. For our purposes, we just take the first row and the second row. Then we say that, look, the probability that one number is bigger than another number in my standard Young tableau. So this is going to be my x, and my y is going to go into the red line right below x and to the left of x. So what I'm saying is that no matter where I choose this number y, that's going to correspond to a point in the plane. And the question is going to be, do the paths, this d-dimensional paths, when they project, they're going to be to the left or to the right, or if you're thinking diagonally, above or below this point A that we get. Now, the way to understand it is the picture is going to be very large. So this is your very large picture. The probability of paths going through any particular point is going to be relatively small. And therefore, what you can do is essentially go from top to bottom and continue going until your probability crosses 1/2. Once, if all the probability, if there is some kind of anti-concentration result, which shows that there is no point where the probability is really, really huge, then you're going to go slowly, and eventually, when you overshoot 1/2, that's the place. That's the place when you take. That is a general. That is a general idea of how this works. Is everyone okay with this explanation? Yeah, I know, very much incomplete. So now we need tools. Essentially, there are two kinds of tools we're using. First is asymptotics of sure functions, and those are unbelievably long formulas. But there is another tool that I wanted to highlight, is this Narus-Hucknang's formula, which together with Alejandro Morales and Greta Panova, we've been working on for a while, and we need an asymptotic version of that. So basically, we can do some calculations of the number of skew shapes, standard Young tableaus of skew shapes, which go into comparisons of these probabilities. That is a very rough idea of what we do. Is everyone okay with the statement and the theorem? Okay. So again, the important part here is that we can do this only when the width is small. In fact, if you take general diagrams, we don't know. So this is something that I wanted to mention. I'll mention later that in fact we do believe the probabilities are going to be small without the constraints on the height, but we just can't do it. So in a special case of Catalan poset, let me remind you that Catalan posets are posets corresponding to Young diagram 2/n. In which case you get Catalan number linear extensions. In that case, we can do better. We can, in fact, show that the sorting probability. So remember, we had big O of 1/√n before, and now everything jumps to 5/4, and that's because we can completely avoid all the estimates with sure functions. In this case, everything can be done with binomial coefficients and can be done rather explicitly. So this is still so there is no so from this point in this proof there is no probabilities involved at all, even though the statement says this is sorting probability. In reality, this proof becomes analytic combinatorial. We just need to look at the estimates that we get from so again, what are the estimates? The estimates become what is the probability that my lattice path, this is the usual lattice path from lower left corner to upper right corner, which counts the number Catalan numbers. So what are the probabilities that these paths go above or below a certain point in my staircase shape? And we show that there exists a way to do it so that this probability is really small, 1/n to the 5/4. But that's all we can do. And is everyone clear about this? So maybe to make a picture for that, the way this works is you shouldn't take two elements which are very close to the beginning. You really should take two elements which are somewhere within square root of n distance to each other, somewhere near the middle of the first two rows, and the calculation becomes somewhat delicate beyond that. Okay. So let me maybe make before I move on, let me make a general conjecture that delta of p lambda is always going to be big of 1 over n. I don't have any idea of how to approach that, but that's how it's going to be. So, so now I'm going to switch gears a little bit, and I'm going to talk about inequalities for the number of linear extensions, and that's another just a fantastic direction which started about 20 years ago with Stanley's theorem. Stanley proved that using Alexander Fenkel inequalities that there is log concavity for certain numbers of linear extensions. Let me tell you what are the numbers. You fix a poset, you fix an element x in the ground set, and now you're looking at the number of linear extensions such that the element x, the linear extension at x is equal to k. Is everyone clear about this? Okay. So, so what we're saying, so what Stanley is saying is that ak square is greater or equal than ak minus 1 times ak plus 1, and somehow there is no way to prove it combinatorially, in the sense that there is no like a natural injection from two pairs of linear extensions on the right to a pair of linear extensions on the left. This is a really delicate inequality which requires geometric arguments to prove. Everyone clear about Stanley's inequality? Okay. So there is a generalization by Kahn-Saks. So they in fact needed that generalization to prove the 511 bound that they had that I showed you for the sorting probability. So what they define numbers a of k a little bit differently. They fix two elements x and y in my ground set, and now they're looking at at linear extensions, so that the difference of the values of the linear extension is equal to k. And then just they get the same log concavity as Stanley gets. So this is, and in fact, it is really easy to see that one theorem generalizes another by taking one of the elements to be the global minimum element in the whole poset. Is everyone okay with this conjecture? I mean, with this theorem? Because what's coming now is the main conjecture, which is kind of remarkable. This is a conjecture by Breitel, Felsner, and Trotter in '95. I already wrote the name before at some point. So this is sort of the next level extension of, so from Stanley you go to Kahn-Saks, and now three people introduce this conjecture for triple of elements x, y, and z. So suppose you have x, y, and z, you define numbers fkl to be number of linear extensions, so that the difference between x and y is equal to k, and difference between y and z equal to l. Okay, so this is sort of next next level. And in this case, the conjecture is open. BFT only proved it for k equal to 1 and l equal to 1, and it's open and full generality. So that's going to be our main conjecture. Dan, you wanted to ask something? No, okay, good. Anyone else? Everyone clear about the conjecture? Okay, good. So that's a conjecture that we're working on, and the way the conjecture goes is we don't know, but you know, it's the usual game one can play. Rather than prove a conjecture, you generalize it. So this is a generalization of the cross product conjecture. Our generalization is basically introducing two more parameters R and J. So it used to be K plus 1 and L plus 1, and now it's K plus I and L plus J. Okay, so generalization of that. And we have a reason. And the reason is we can actually prove something. But before I tell you what can we prove, let me tell you why this is so remarkable. So this cross-product conjecture and its kind of mild generalizations that we have is, first of all, it implies Kahn-Saks inequality, which in terms, as I mentioned before, implies Stanley inequality. Next, it also implies Graham-Yau-Yau inequality for poset of widths 2. I'm not going to tell you what it is for the lack of time, but you just have to trust me. That's another very interesting inequality for posets. And but more kind of excitingly, it implies the XYZ inequality, which is a theorem. It's a theorem by Larry Shepp, which says the following. He is using the same three letters XYZ to say, now let me sort of make sure that you can see the bottom of the slide. What this is saying is that if you have three elements X, Y, and Z, if you condition that f of X is less than f of Z, then the probability that f of X is less than f of Y can only go up. So introducing some inequalities between X and some other element kind of pushes this element to be f of X to be smaller, which turns out to be true and can be rigorously proved. Is everyone okay with this inequality? Yeah. Everyone okay with this? If you're not okay, there is a really nice historical article Peter Winkler wrote, from which I learned the struggles he and a bunch of other people had in order to prove the XYZ conjecture, which later became Shepp's theorem. And thank you, Peter, for writing that. That was illuminating. So everyone okay with Shepp's theorem and the XYZ inequality? Any questions about any of that? Before I tell you our results, we're getting close to the end of the talk. Okay. Okay, good. So the general point is if you generalize cross-product conjecture a little bit to introduce this I and J, then you can start doing miracles, and we cannot prove generalized cross-product conjecture for all posets, but we can prove it for posets of width 2. That is our main result. So not only we can prove CPC, but we can prove generalized CPC in this case. And but we can also get a Q analog of the usual CPC. Let me define the Q analog for you. So as I mentioned before, there is a way to partition. If you have a poset of width 2, there's a way to partition into two chains, and one can just define the weight of a linear extension as a sum of the values of linear extension on one of the two chains. Doesn't matter which one. And now we can define a Q analog of those numbers, FKL. Basically the same summation as before, but you introduce Q to the power this funny way. So when you get Q equal to 1, this is going to be the usual F1 KL is the usual FKL. And what we can do is we can prove for posets of width 2 this inequality which has polynomials now. So rather than the so without when q equal to 1, it's the usual CPC. When for general q we get polynomials. And the way we're writing this inequality is what we mean is that the difference between these two polynomials has no negative coefficient. So this is an inequality for coefficient wise. Is everyone clear about what we're saying? Now I should mention that that the two proofs of that result and this result obviously those are different theorems, but they have the same CPC in common, and there are two completely different proofs of CPC. One uses a sort of dynamic programming idea turned into linear algebra, and we're doing everything using matrices, and at the end of the day, turns out that minors of a certain matrices are non-negative. And for the second, for the Q analog, we're using lattice path, which is a little bit similar to the technologies that I described in the previous pages. And finally, I want to mention some more conjectures, because if you can, again, as I said, if you can prove conjectures, generalizing them is just a fantastic thing to do. So one thing to do is to try to merge these two approaches together and try to obtain Q analog of generalized cross-product conjecture. That's probably going to be true. Another approach is to ask for an equality, and we're sort of working on the on both 1 and 2. Is that true that if generalized CPC is true, then in fact let me remind you what generalized CPC is. So if you have this inequality over there, then turns out that we believe that this can only happen if one term on the left is equal to one term on the right, and another term on the left is equal to another term on the right. That's what we believe is happening for the equality. And our final, more speculative conjecture is that we actually believe that this 2x2 determinant, which you can see in the CPC, in generalized CPC, are actually indicative of the whole matrix to be non-negative definite. Which means that all if you have to write K in one order and L in another order, but the point is that all minors are going to be non-negative and we can prove that, but we've checked it for posets of decent size that seem to be true. So that's so there's some computational evidence in favor of this conjecture, and that's it. That's where I stop. Thank you all.
Any questions or comments?
Very nice, Igor. This is, I know this is a very tough area to make progress in, and you've done some great stuff.
Thank you.
Going back to this skew tableau, so the result here is that there just finds one pair, right? So original motivation, you'd like to have a class which is preserved by adding extra edges so that you could reapply the theorem and show that you could sort one of these guys in only 1 plus little of 1 times log base 2 of the number of linear extensions. But you can't do that here unless you have more than just one pair, or you have some recursive thing. I don't suppose that you can get more than.
So we don't actually deal with that at all. The whole thing is there exists a pair, one element as I drew lying in the top row, second element lying somewhere in the second row for which this is true. I suppose because one can do one can run the it's a Markov chain. One can estimate these probabilities and one can find them more directly. We haven't tried that, and in general, we sort of consider the problem of effective sorting done. Kahn-Kim theorem solves this. It doesn't negate the problem of what's going to happen for general posets. And since we happen to know quite a bit about young tableaus, that's what we did.
Oh, very nice. I just wanted to mention a story that you might have heard, but you might enjoy, that when Leonid Khachiyan presented his algorithm for estimating the number of linear extensions, so he was visiting Rutgers, where he later got a position at the time. And he was this big, bear-like guy with a huge Russian accent, of course. And at the end of his talk, someone asked him whether his algorithm was robust. And he said, "Robust? You want to know whether my algorithm is robust? It works on Russian computers."
I did not know that. But that's a compliment.
Are there any more questions or comments? Okay, let's thank Igor again for a very nice
Thank
talk.
you.
Okay. All right, I'll stop the recording now, I guess.